I'm just gonna start off by running it. So we can see it comes up with user text interface where you're able to choose an algorithm. So I'll choose breadth first and choose easy. And I can see it spits out the solution. It starts with the solution node, the goal node, and moves backward until the root node and displays some things like the action it took to get there, the path cost, and the two different heuristic values. So I think we can jump right into the code from there. In order to model the 8 puzzle, I decided to use a node. So within that node, it has the state of the puzzle at that point. So I'll just go into there to show that the state is recorded by a list of integers, and then we also have the blank int, the location of the blank integer recorded just for kind of convenience here. But yeah, this list represents each position in the puzzle and the number in that state, in that place. Yeah, and then in the node we also have the action that was taken to get to that state, the path cost up to that point, and then some heuristic values and the parent of that node, so we can trace the path back. I think the next thing to show would be the state transformer class. This is how I moved between different states. I called it a transformation. So the initial node is passed in and the action that's supposed to be taken on that node, and then based on that action we'll perform one of these functions. So we'll basically move around the values in that list based on the action, and then return a new node with that new state in it, the action again that was taken, and then the updated path cost, which is the path cost of the parent plus the new value that was just moved. And then we also calculate new heuristic values for that new node. So I think we can go into one of the solvers now. I'm going to do the depth first solver as the example here. So when we go into the solve method, we check if the node that is passed in, the root node, is in the goal state. So we're just checking that it is, whether or not it's equal to this this hard-coded list that is the goal state here. Then after, so if it is the goal state, we return it, but if not, we're going to move on to creating this stack to explore. So this is the queue that we talked about of the nodes that we're going to explore and which order we're going to explore them in. So for the depth first solver, I used a stack so that the first nodes that go in are the last nodes to be explored. So I add that node, I do this update max queue to keep track of the max queue length, and then I go into this while loop. So while there are nodes to explore in this stack, we are going to pop one off the top. So pop the newest added to the list, to the explore stack off. Add that node to the explored hash set, so a unique list of any states that have already been visited. And then we're going to go into this for loop here, which we get all of the possible actions that can be taken based on this current state. And then we create a child node for each of those actions. And basically, if that child node has not already been explored, or it is not already in the to explore queue, then we are going to check if it is itself a goal state. And if it is not a goal state, we will, so if it is a goal state, we'll return it. If it's not a goal state, we will push it onto the stack to be explored later. And then we'll go around and pop off another node off the stack. So one thing to note here is that in the case of, for example, the breadth first solver, I used a queue so that the first nodes that go in are the first nodes that come out. And then for like the heuristic solvers, I used a priority queue so that that queue could be ordered by a given heuristic, so that those nodes with better heuristics could be explored first. Yeah, so that's my program. Thank you.